my pleasure to introduce Emily, who's going to tell us about the future is real-time data. Let's welcome Emily.
So hi everyone, thank you for joining me today on this presentation about real-time data. We're going to be talking about this technology called stream processing, which is a specific way that we process data. I'm Emily. I was previously a technical writer and developer advocate at RisingWave Labs, where they were building RisingWave, a stream processing database, and we'll get into exactly what that is a bit later. And there I was working on documentation and just building runnable demos to showcase how RisingWave and stream processing can be used in different industries. So today we're going to be exploring stream processing, a powerful method of data processing that allows us to work with information as soon as it's generated. As our world becomes more data-driven, organizations, companies are generating massive amounts of data or getting massive amounts of data every single second. So think of like your finance industries, your e-commerce industries. So the ability to process and analyze this data instantly is crucial for making fast and informed decisions. So today we'll be breaking down exactly what stream processing is, comparing it to our traditional method of data processing known as batch processing, and then going into talking about where stream processing is used exactly in real-world applications. And then we'll be moving on to how to build a data pipeline that's suitable for stream processing, like the different types of data platforms that you'll need. And then at the end, I'll go through a live demo of what that data pipeline would look like and how stream processing looks like in action. So to start, what exactly is stream processing? Stream processing is a method of handling data where we continuously ingest, process, and analyze information as it arrives. So instead of waiting for data to collect over a specific period of time, stored, and then analyzing it, stream processing enables real-time insights and immediate responses. So the traditional method is great for large-scale analytics, but it introduces latency, so your decisions are made based on older data. This works in certain cases and is probably applicable in most of our general use cases, but in stream processing, this is perfectly suitable for cases where you need to process real-time data. And a key concept in stream processing is the data stream. So instead of working with files or buckets of data, we're working with data streams, which are continuous flows of records representing individual events. Some examples can be like clickstream data, where you're tracking user interactions on a website or app in real time. Financial transactions, where you're monitoring payments looking for fraudulent activity. IoT sensor data, where you're analyzing environmental conditions, equipment performance, or smart home devices, or login telemetry data, so you're observing system health and security threats in real time. So now that we've established what stream processing is, let's compare it to batch processing. So if you're already familiar with just general data processing and data pipelines, the concept of batch processing might come to mind. Usually if you're doing any sort of reporting, creating ETL pipelines, or creating machine learning workflows, you're probably using batch processing. So let's compare it so you get a better idea of where stream processing stands. So batch processing is a method of data processing where we're collecting data over a specific period of time and then processing it all at once. This is usually done on a scheduled basis. So this could be hourly, daily, weekly, monthly. And since batch processing handles data in bulk, it's very efficient on large data sets, and it doesn't require continuous monitoring since, unlike stream processing, data isn't coming in consistently. However, it does introduce the concept of latency because you only get the results after an entire batch of data comes in and is processed. So if we think back to stream processing, data is continuous and it comes in real time. Batch processing comes in chunks. And then in batch processing, higher latency, stream processing, lower latency. And lastly, batch processing is generally more resource efficient because you can choose when to process that data. So you can pick a particular time where your device, or where more resources opened up so you can use it to process this huge amounts of data. But in stream processing, you don't really get to choose when to stop the pipeline if your data is coming in constantly. So to make this idea more concrete, let's think of a particular example where stream processing is better and when batch processing may be better. So if we think about the finance industry or the banking industry, and we want to monitor for fraudulent activity, when it comes to batch processing, it may not be that efficient or that useful if we're only able to find fraudulent activity after like an hour or a day. You ideally want that notice to come in instantly. So in that case, stream processing would be perfect because you can process your data down to the second or millisecond and inform your customers whenever something fishy comes up. But if you're looking at your monthly budget or your quarterly report, then there's really not a point to use stream processing to keep up with what your budget looks like every single second. You can do it on like a daily basis or a weekly basis based on whatever you need. So while batch and stream processing seem like completely two different approaches, they actually exist on a spectrum where somewhere in the middle we have micro batch processing. So earlier I said that batch processing, usually the data comes in like hourly or daily. You might have the idea, well, what if we just break down those batches into like really, really small batches, like minutes or seconds? And that's exactly what micro batch processing is. It's an approach that aims to minimize latency while still maintaining some of the efficiencies of batch processing. And since these batches are broken down into really, really small time segments, this makes it almost near real time. But usually these batches aren't going to be any smaller than a second. If you can get your batches down to a second, that's already going to be very efficient. And most frameworks that do support micro batch processing, you probably can't get it down to a second, especially if you're getting in a lot of data. So stream processing, on the other hand, you can get it down to subsecond to like milliseconds. So none of them are like the correct way to process your data. It really depends on exactly what you're trying to achieve. So if you need high throughput, like if you have a lot of data and you don't really need real-time insights, batch processing is perfect. If you want low latency but some delays are okay, then micro batch processing is perfectly fine. And if you just need whatever is the fastest possible, like I need this result right now based off of whatever's the freshest data, then you would want to choose stream processing. All right, so now that we have a solid understanding of how stream processing works, let's talk about exactly where people are using stream processing. So I've broken this down into 4 categories. Streaming analytics, where we're extracting real-time insights from fast-moving data. Event-driven applications, so systems that can react immediately to events as they occur. Real-time data enrichment, where we're adding additional context to our data streams, and feature engineering for machine learning models. All right. So let's start with streaming analytics. So this is usually when you have high velocity data streams and you want to continuously process and analyze that data for instant insights. And this is probably most applicable in the stock trading and algorithmic trading. So financial markets are generating an enormous amount of data every single second. I'm sure a lot of us look at the NASDAQ stock tickers throughout the day, and it's changing every single second. So stream processing enables us to process that data in real time. We can look at the market trends, the order books, and the price movements as they happen, and we can process that data, analyze that data, and it enables traders to make split-second buys or sell decisions. And then another good example would be sports betting or like live event tracking. If you're looking at any type of live sports, things are changing and happening very rapidly. So you want a data processing system that can process those data points and allow you to understand what's happening. Or if you're doing like any sorts of sports betting stuff, those betting odds would be adjusted dynamically to allow your users or your audience to get the latest insights. And another example would be IoT monitoring, so sensors in industrial equipment. If you work in any sort of lab, you probably have those like temperature trackers just to make sure that whatever environment you're in is at the optimal temperature and humidity. And cybersecurity, again, you're just monitoring network traffic, and you want to do that constantly, and you want whatever's the freshest data so that, if anything happens, you'll be notified instantly. Then the next use case that I had up was event-driven applications. So event-driven applications is when you're reacting to the events as they happen. So rather than just looking at whatever statistics is popping up, you're actually doing something or the program that you're building is reacting in response to that. So many modern applications, particularly in microservice architectures, are built around event-driven processing, where different components listen for and respond to real-time data. So some examples could include like fraud detection in banking. Banks can analyze transactions as they occur and flag suspicious activity based on real-time user behavior. So if they know that you're in one state, but for some reason a transaction from a completely different state or country pops up, they can notify you instantly. Another example would be like customer engagement. If you pull up your Netflix account, your recommendation is going to be constantly changing based off of your previous views or just whatever user profile they've built up around you. And then system monitoring, so IT teams can monitor logs and performance metrics in real time, and if a web server starts experiencing an unusual amount of traffic, they can automatically trigger something to help the system before everything crashes. And next, we have real-time data enrichment, and this is mostly just combining your incoming data streams with external or historical context to enhance decision-making, and this sort of goes into the concept of a hybrid batch and stream model where you're able to process both streaming data and batch data on the same platform. So this could be very useful in like ad tech and like advertising, when an ad platform bids on an impression in real time, it can enrich raw bid requests with historic user data, browsing behavior, to determine the best ad to serve. E-commerce, so any online store can dynamically adjust prices based off of like real-time demand or user behavior so that they can maximize their profits. Or supply chain and logistics. So in this case, shipping companies can use real-time data to optimize their delivery routes based off of existing traffic conditions and weather forecasts and fuel costs, so that their operations are running at peak efficiency rather than just going through the same routes every single day or trying to optimize those routes after something has happened. And the last use case is going to be feature engineering for machine learning. So This is a more advanced application of stream processing since you do have to combine it with a machine learning model. So in machine learning, features are the inputs that models use to make predictions. So for real-time applications, these features can be generated instantly as new data arrives instead of being built previously on old data and then just using the same few features over and over again on new data. So some good examples would include like AI-powered customer support bots. I think they're becoming a lot more popular now on a lot of sites where you go on the website and instantly a text box pops up and you're chatting with a chatbot instead of an actual person. But we can improve these chatbots by employing stream processing, by having the chatbot react to real-time user interactions, use sentiment analysis and historic customer data to adapt their responses. And since we're using stream processing, they can continuously learn from new interactions, ensuring that feature vectors and the machine learning model is always up to date based off of our newest data and how our current customers behave. Another good example would be real-time risk assessment. Specifically, if we think about like the healthcare industry, this would allow for better patient care, enabling faster response times, better predictions, and improved patient outcomes. Healthcare providers can extract features from real-time data sources, such as any type of wearable devices, ICU monitors, and electronic health records to prevent critical medical conditions before they escalate. So instead of using like historic data and gathering all of that data in one place, they can update their analysis consistently to ensure the fastest possible decision-making process. And then the last example I have for today, in this case, is going to be predictive maintenance. So sensors on industrial machines can continuously generate telemetry data that which can include vibration patterns, temperature fluctuations, and like efficiency metrics. And you can transform these data points into real-time features that help you predict equipment failures before they happen. And this will make the entire operation more efficient so that you don't have to schedule maintenance based off of fixed intervals. Instead, you can be more proactive and prevent failures from happening before they actually do. So now that we know where stream processing can be used, let's talk about when you shouldn't use it, because it's not the only choice out there. So some use cases where you don't want to use stream processing would be any type of large-scale historical analysis. So if you're running like annual business reports on like a huge amount of historic data, there's not really a point to use stream processing because you can just use a batch processing platform that's going to be much more efficient and save on compute resources. Another one would be ETL workflows for data warehousing. So a lot of organizations just use batch pipelines to manage that data for offline analytics, and it works perfectly fine. There's not really a reason to like change over to a new method. And the last one that I have is going to be regulatory reporting and compliance. So some industries have strict compliance requirements, and you're not going to need real-time processing for that. So in any of these cases, it's really going to be dependent on exactly what your requirements are in regards to latency and what resources you have available in terms of actual compute resources as well as like actual human labor. All right. So now we can move on to how to actually build a data pipeline that enables us to do real-time data processing. So unlike traditional pipelines, a stream processing pipeline needs to handle continuous unbounded data streams, and unbounded data streams are just streams of data where there's a specific beginning, but there's not a specific end. So it can keep on coming in forever, and you'll need a way to deal with that. So to handle this efficiently, we will need several key components: a pub subsystem to ingest and distribute streaming data, an actual stream processing platform where we can transform, enrich, and analyze the data, and a storage layer to process data for like future use. So let's start by breaking down each of these components, starting with the pub subsystem. So a publish-subscribe system is a messaging infrastructure that allows data producers or publishers to send messages to a central broker from which data consumers or subscribers can receive them in real time. So instead of directly connecting producers and consumers, pub subsystems act as an intermediary layer, ensuring that data flows smoothly and efficiently between them. So why do we need this like in-between layer? Because wouldn't it be easier to just skip that part and just send it directly to our processing framework? So decoupling our producer and consumers is actually a good thing, because instead of sending data directly to an analytics system, this creates this dependency between your producer and consumer. So if your analytics system is down or slow, the producer either has to wait, or if it's down, then you just lose all of that data in between that time. So a pub subsystem removes this bottleneck by allowing producers to send data asynchronously while consumers pick it up at their own pace. And that just makes everything a bit easier. And it allows you to handle high velocity and high volume data. So many applications can be generating thousands up to millions of events per second, and it can be difficult for your analytics platform to directly consume all of that efficiently and process all of that. So this pub subsystem acts as a buffer, ensuring that no data is lost while it's being processed. And it also enables multiple consumers. So a lot of the times companies have like multiple use cases using the same data stream. And so having this pub subsystem allows different teams to ingest specific parts of that data, and they can use it for whatever they need. So an example could be like a stream of e-commerce transactions can be used for both fraud detection, recommendation systems, and operational monitoring. And for each of those cases, you're probably not dealing with like the exact same data set each time. So having that pub subsystem makes it a bit easier to just choose which streams of data or which sections of data you want, and then process it more efficiently using your processing platform. And lastly, the pub subsystem allows for fault tolerance and scalability. So if one consumer fails or slows down, the pub subsystem is able to store the messages until it's back online. And most modern systems are distributed, so you can scale them across clusters for further fault tolerance and also for scalability. So let's talk about two of the more popular open source frameworks. The first one being Apache Kafka. So if you've ever worked with streaming data or not, you might have heard of Kafka. It was originally developed at LinkedIn, and it's designed to handle high throughput real-time data streams reliably and at scale. Right now, it's sort of like the de facto standard for distributed messaging, and it's used across a lot of popular industries and at very well-known companies. So at its core, Kafka is a distributed event streaming platform that enables applications to publish, store, and consume messages in real time. Unlike traditional message queues, Kafka is fault tolerant, scalable, and designed for high availability. So Kafka allows your messages to be persisted allows your messages to be persisted because it's built on a distributed log-based architecture. So the messages are written to append only logs, and stored across multiple brokers. So this allows Kafka to retain messages for a configurable period, so that could be minutes, hours, or days. And this allows consumers to replay past messages without affecting their performance. So if a system goes down, they can pick up where they left off. Secondly, Kafka scales efficiently using partitions. So whenever you get a message is stored within a specific topic, and then that topic is split up into multiple partitions, which are then spread across brokers. This enables for parallel processing, making Kafka ideal for handling high throughput data streams like financial transactions or order processing. So just to sort of just to sort of like summarize things, so the key features of Kafka include like its high throughput, scalability, persistent storage, and strong ordering guarantees. So messages within a partition are strictly ordered, but because topics have multiple partitions, ordering between partitions are not guaranteed. It's only within the partitions. And a rich ecosystem. You can easily connect Kafka to a lot of different other frameworks. And for the sake of time, I am going to skip over Pulsar. Pulsar is just another option, and it's very similar to Kafka, but it has a 2-layer architecture, a broker and a bookkeeper. So brokers just handle real-time messaging. So they take the message from whatever publisher you have and then send it off to a consumer. And then the bookkeeper is in charge of storage. So that means you can scale them independently of each other. You can scale the storage layer without increasing the number of brokers you have. And one point to mention is geo-replication. So the architecture natively supports cross-region replication, allowing data to be mirrored across multiple data centers without complex configuration. On the other hand, for Kafka, if you want to do that, you're going to add in additional components independently. And one of the last key feature to mention is the message TTL policies. So Pulsar will automatically clean up old messages to optimize storage. So that makes it a bit easier on you, and you can save on your storage resources. And at the end of the day, whatever you want to choose, it's going to be dependent on your use case. If you just know you're going to have a lot of data, then Kafka is probably going to be a better fit. And Pulsar is ideal for like multi-tenancy, geo-replication, and dynamic cloud scaling. Right. And then the actual processing part of the pipeline is the stream processing platform, which is a specialized system that allows you to analyze, aggregate, and filter event streams as they arrive. Unlike traditional batch processing tools, this stream processing platform is going to operate continuously without stop. And since it operates in memory, it allows for low latency processing, so just doing things really quickly, event time handling. A lot of times your data streams are going to have a timestamp associated with them, and for many use cases, ensuring accurate analysis based off of when the event occurred is very crucial. And lastly, stateful computations, so that just means you're able to keep track of ongoing trends in the data system. All right, and then I'm going to briefly cover 2 stream processing platforms, first being, this is just what the stream processing platform, its position in the data pipeline. So it's ingesting data from various data sources or brokers or databases, doing the analytics within that platform, and then you can offload it to a storage platform that you're using or a data visualization platform. So to start, I'll briefly cover Apache Flink. So one of Flink's biggest strengths is its ability to perform stateful computations efficiently. Flink can maintain state across events, making it ideal for applications that need to track changes over time. And in order to ensure proper time ordering events, Flink uses watermarks, which act as timestamps that track event progress. And this allows Flink to wait for late events within a specified time window, order events properly, and prevent incomplete results. And one key feature to mention is exactly once semantics. And this just ensures that every single event that comes into the system is processed exactly once, and this is mostly done for the sake of accuracy. And it is, I think, one of the more well-established stream processing platforms, so there's a very well-established ecosystem and community, so if you ever have a question, it's probably answered on Stack Overflow already. And next, I'll be talking about RisingWave. RisingWave is a stream processing database, so on top of the processing part, there's also a storage layer so that you can persist your storage results afterwards. The storage and computing nodes are decoupled, so you can scale one without the other based off of your current use case. It is Postgres compatible, so if you want to hook RisingWave up to any other platform, you can do so using the Postgres wire protocol, making it really easy to integrate it into any sort of data pipeline that already uses Postgres. It's available as both open source or cloud. Open source, that just means you can download it, run it as is, and cloud if you want a managed version, so you don't have to deal with any of the setup. And it handles both batch and stream processing, so you can run ad hoc queries as you need on batch data. And one thing to point out is that it is SQL native, so all you need to learn in order to run RisingWave is how to write SQL queries, which makes it really easy for most people who are already familiar with data processing, since SQL is probably one of the more popular languages taught. So just a little bit more detail about what RisingWave is. It's a distributed SQL stream processing database, and it's purpose-built for processing streaming data. And the community is ever growing. And again, I've touched on quite a bit of this already, some of the advantages of stream processing using PostgreSQL, since again, Postgres is such a popular relational database. It's really easy to just get started with RisingWave, since a lot of it is going to be exactly the same. Right? And again, if you're choosing the right one for you is going to be dependent on what you need to do. Flink's advantage is that it does allow for a little bit more advanced transformations. On the other hand, for RisingWave, you're a bit more limited since you're mainly using SQL. You can create some user-defined functions, and that allows you to do a little bit more advanced transformations, and you can include external libraries from Python and Java if needed. And the last part of the pipeline is going to be your storage or a dashboarding layer, and this is going to be optional based off of what you're doing. So since RisingWave also has a storage layer, you don't really need external storage if you don't want to. But if you do need it for whatever other applications you're building, RisingWave does have a very diverse set of connectors that allows you to offload your data to different platforms, whether it be some sort of time series database, Apache Iceberg, Amazon S3. And dashboarding is probably going to be a lot more popular. Most stream processing platforms don't have a built-in visualization part. So if you do want to create dashboards to easily monitor your system, you can attach them to a dashboarding platform such as Grafana or Apache Superset to build your dashboards. All right. And now that we talked about how to build a pipeline, I'll go through a live demo of what that pipeline can look like. So For the context of this demo, we're going to be sort of simulating a energy company, so sort of like PG&E, and how they would monitor a community of homes and each home's energy usage. And so our data pipeline is going to include a data generator for the sake of this simulation, and that's just going to simulate how much energy each household is using every single minute. And then we'll have Kafka as our broker, and then we'll also be using Postgres as additional storage for some of the customer data, so what type of plan they're on, what address they're at, stuff like that. And then we'll be using RisingWave as our stream processing layer to transform that data to get meaningful insights on how much energy each house is using, and predicting their monthly bill at the end of each period. And at the end of this pipeline, I'll have a dashboard set up that allows us to easily monitor all of these things. All right, and I'm just going to switch over the display. Okay. Right, so this demo is available at the RisingWave GitHub repository under the awesome stream processing repo, and you can find it under solution demos, energy grid, and you can pull this bit of code to your device and run it as is using Docker. I think the only thing that you'll need to install is PostgreSQL. Any version that is earlier than 16 is going to work perfectly fine for this. So we can go ahead and start it up. I was testing it earlier today, and this will start all of the necessary components. And for this demo, I have Zookeeper and Kafka as our pub subsystem. Kafka uses Zookeeper to run. And then the Kafka producer is our data generator that's sort of simulating 20 households' energy usage throughout time. And then our RisingWave instance to process data, and then the Grafana dashboard. I also have the Postgres database set up, as well as this is just the script to create a table in Postgres and ingest it or inject some data into it. Right? And then to start RisingWave, since this RisingWave instance is already started, I can open up a terminal shell here. And these are just the default parameters you use to get access to the RisingWave database. Right? And once we have RisingWave started, all we need to do is, I already have the code ready here in the GitHub repository, so it's a lot easier to test out this demo. So we'll start by connecting to our sources. So in order to connect to any sort of data stream, so from like Kafka or Pulsar, we can use the create source command here. And here we just define the schema of the data, so what columns you have and what data type they are, and the connector parameters, so what type of connector are you using, what topic you're consuming from, the Bootstrap server, and you can further customize this by specifying from exactly which time point you want to start consuming data from, and like security authentication options are also available, but for a demo, that's not really necessary, and we can just copy those over. So when you create a source, you can't really query from it just yet because it just creates that connection. It's only after we create a view on top of it, or a materialized view in this case, where it actually starts ingesting data. However, if you do want to also store this data within RisingWave, instead of using create source, you can use create table, and everything else is the same. So a table persists the data in RisingWave a source just creates that connection. And then in order to connect to our Postgres database, it's going to come in two parts. So first, it's going to be a create source command that won't copy over. So that creates a connection to the Postgres database. So that will include like any sort of login credentials you used for this database, the port you're on, the username, the password, the database, and then because a lot of people have multiple tables that they want to ingest data from, you can then create tables based off of this source, making it a lot easier if you want to ingest data from multiple tables. So the source creates the connection, the create table actually ingests data from the Postgres database. And this is a CDC connector, which means that if you make any changes to your source Postgres table, those changes will also automatically be reflected within RisingWave. And in this case, you can query from the table. So if we just count the number of customers, we'll see that we have like 20 households set up. So once we have our sources, we can start creating materialized views. So a materialized view stores the results of a query, but the difference is that it's going to be constantly updated as new data comes in. So it's always going to give you the freshest results based off of the freshest data. And one extra feature that I added here is a user-defined function that counts the number of days that are within each month. So some months have, I think in Postgres there is a built-in function for this, but it doesn't exist yet in RisingWave, so I had to define the logic separately, which is not copying over. And then we can start creating materialized views to track different aspects of energy consumption. So in the first case, this just tracks the amount of energy each household is consuming within 5-minute intervals. In this case, I have both a energy. So it actually stores the results of your query, and it gets updated every time new data comes in. So it's always going to be like the same set of data, it just gets updated. Yes, these are updated automatically. Yes. 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 So in this particular demo, I have the households both consuming and producing data. So producing in the sense like, oh, they have solar panels. So this calculates the net consumption, which is going to be the amount of energy that they consumed minus the energy that they produced. And then we can just query from it, just to see what that looks like. So since it is midnight, there is no energy produced. Since I'm assuming they're using solar panels, there is no sun. And then the next query is going to be keeping track of how much energy they've used throughout this month. And this notice just is about the time zone that I'm setting. I'm not using a time zone, so it's just automatically going to be set to UTC. The next two queries separates the customers based off of what payment plan they're on. So if they're on a tiered system, it just calculates their monthly bill based off of the total amount of energy they've consumed. If they go above a certain amount, they're going to be charged more for each unit. And then the other one is going to be time of use. So the amount they're charged per unit of energy is going to fluctuate based off of what time of day it is. So during peak hours, they're going to be charged more. And then the next few queries are going to be calculating the bills for each customer based off of what payment plan they're on. So the first one is going to be calculating their current bill for tiered customers, and then the next one is going to be estimating the bill at the end of the month for the tiered customers. And this is just going to be a really simple estimation based off of average usage so far over the month. And then we're going to be doing the same thing for the customers who are on a time of use plan, the same pay bill so far, and then estimated bill at the end of the month. Right? And then once we have all of those queries set up, we can then open up this Grafana dashboard that I've already set up with all of these visualization panels to keep things easier for everyone. So these are just basic summaries of the current monthly usage throughout the entire community and the estimated monthly usage at the end of the month. And here we're just keeping track of the simulated time within the data generator. So right now it's on May 2nd, 1997. And again, just keeping the net consumption throughout the entire community for this hour, for this day, and then for this month. And the consumption is going to fluctuate throughout the day. If there's nobody at home in the middle of the day, there's less energy used. Also, there's less energy during this time because the sun is actually out, so the solar panels are collecting energy, so the net consumption is going to be much lower. At night, people are home, there is no energy produced, so the net consumption's a bit higher. And then same thing here, net energy consumption throughout all of the 20 households throughout the day. It's higher at night, and then higher at night, lower in the middle of the day. And since we're still going through like this period of time, this data point isn't fully updated. Same thing here, just average energy consumption. And then at the bottom, we can compare the bills between the two different payment plans, where the tiered customers, we see that their current bill is lower, but their estimated monthly bill is going to be higher at the end of the month compared to the customers who are on a time of use payment plan. Their estimated monthly bill is going to be lower. And since I am using a data generator, there's not too much variance between how much energy each household consumes. So the total energy used so far and estimated total energy use is going to be pretty much the same. So yeah, if you do want to test out this demo, again, it's available at the RisingWave GitHub, RisingWave Labs GitHub, awesome stream processing repo under solution demos, and the energy grid. Just minor caveat, when I initially set this up, I didn't specify a version for Postgres. I think right now if you automatically pull it using Docker, it pulls version 17, which isn't compatible. So you will need to change that here, just anything under 16. I chose version 12, and everything will work just fine. And yeah, that's it for this presentation. Thank you all for coming.
Questions?
Thank you for the presentation. What is the flow of messages in this demo? So the publisher publishes the message to Kafka, and then does RisingWave store the message for some period of time?
So in this case, RisingWave does not store the raw message because I used a create source statement. If you do want RisingWave to store it, you can use create table. But once you actually process the data and start creating materialized views, all of these results are stored within RisingWave.
And updated on every new message.
Sorry?
And the view is updated?
Yes.
More questions? I don't see any more questions, so let's take the opportunity to thank the speaker again.